California's water supply is severely impacted by the snowmelt hydrology, snowmelt runoff. And in the western United States, over 50% of our water supply is generated from snowmelt runoff. And in California, that number is about 30% during a normal year. And that's because the snowpack acts as a reservoir. So when the snow falls, the snowpack stores the precipitation during the winter months and then releases it in the spring when we need it during the dry season. And we'll often use computer models to predict the timing and the amount of snowmelt that occurs. And that's of utmost importance to our water supply forecasting, our flood forecasting, and our water resources management. So if you've been paying attention, there's been some recent media attention on the latest snow survey that took place in January, where our snowpack is finally above average, above normal. And that kind of inspired me to go back to my thesis work that I completed in 2011, where I looked at just one particular parameter of a snowmelt model. But what I wanted to do here is just present some background material that I conducted this really extensive literature search just on how snowmelt actually occurs. So that's what I wanted to present to you today. And so the snow falls in the winter season and it accumulates into the structured snowpack. And then at the onset of the spring months, it starts to melt. Well, how does that happen? And the answer to that is the snowpack actually undergoes snowpack metamorphism. It evolves as the season progresses. So at the beginning of the winter season, when a snowflake falls from a cloud, its edges are really pointy. There's very abrupt edges. There's about six sides to the snowflake, and there's a lot of space in between each of the edges. And then when it falls and it creates the snowpack, it's not very dense at all. There's a lot of air in between each of the particles, in between the void, the pore space. But as the season progresses and evolves, the snowpack compacts, it densifies. Those sharp edges start to round. Particles start to clump together and they get bigger and bigger. The pore space starts to get smaller, and the snowpack compacts and densifies. The ice crystals start to consolidate, and at that point, the snowpack is able to yield water and runoff. Fresh snow has a density on the order of 10%, while aged snow, which has had time for the metamorphic processes to unfold, has a density much higher, 45 to 50%. One of the metamorphic processes that allows for this is really interesting, freeze-thaw cycles. This happens around February or March when the temperatures are a little bit higher. But so within the snowpack matrix, there's both large and small particles. And the smaller particles will melt during the day, and that melted water will adhere to the surfaces of the larger particles. And then at night, that whole unit will freeze. And then in the morning, temperatures will warm again, it'll melt again. So these freeze-thaw cycles will continue, and that will allow the particles within the snowpack to get bigger and bigger. So bigger snowpack particles, ice crystals, allow for more absorption of the sun's radiation. Solar radiation is the principal agent that's responsible for snowmelt. And as the season progresses and we get a denser snowpack, that denser snowpack is able to absorb more solar radiation. At the beginning of the season, with fresh snow that's clean, often has a white color. That snowpack does not absorb a lot of solar radiation. Instead, it just reflects it. But as the season progresses and the snowpack compacts, that snowpack is able to absorb more solar radiation. And another interesting phenomenon is that the temperature within the snowpack will actually evolve through the season as well, so that in the upper layers at the beginning of the season, in the upper layers we have temperatures that are sub-freezing, very, very cold, but as we get into the deeper layers, the temperature's warm because the deeper layers are a little bit more insulated. But then as the season progresses and the snowpack evolves, the temperature will be warm throughout all its depths. And then likewise with the density profile, it too will evolve as the season progresses. So at the beginning of the season, fresh snow, which falls at the top layers of the snowpack, will be less dense just because it's fresh snow. But then as we get deeper into the snowpack, the deeper layers will be more dense because that's where the metamorphic processes will have had the time to unfold. As the season progresses, though, the density of the snowpack will be high, will increase throughout all the depths of the snowpack. And the implications of that are, in the springtime, we have a smaller snowpack. And that smaller snowpack is more dense than the winter snowpack. And therefore, we're able to extract more water out of a smaller, shorter snowpack in the spring relative to the winter. And then there often comes a point in time when the liquid water that's held within the snowpack exceeds the force of gravity, and then that snowpack is said to be ripe. And at that point, the snowpack will start to release water from its base, and that's when we start to get snowmelt runoff, which ultimately supplies our rivers, our reservoirs, and our groundwater systems. So with that, thank you for the opportunity to allow me to revisit my prior work.